So this talk is going to be centered around this challenge from the 3-month hackathon I mentioned, the Machine Learning Marathon. It's called WattBot, Estimating AI Emissions with RAG. This is hosted on Kaggle, so it's open to the public. Anyone can join. We had around, I think, 20 people at UW-Madison who engaged with the project. The setup here is we want to build a chatbot system that can accurately answer questions about the environmental costs of AI and produce credible citations that back up its answers. So how can we do this? One way that's become very popular over the past couple of years is retrieval-augmented generation. So here's a one-slide overview of what retrieval-augmented generation is, or RAG. If you haven't heard of it before, this is an improvement upon regular large language model generation. So if you talk to just a standard large language model, you ask it a question, it's going to generate an answer that's based on that model's training data. So it's going to generate a response that looks like what it's seen in the past in its training data. And that could be the correct answer, or oftentimes it could be the wrong answer. And so although large language models tend to sound intelligent, in their base form, they can get lots of things wrong. And I'm sure lots of you have experienced that over the past couple of years. So with RAG, what we try to do is rather than just blindly asking a question to a large language model that generates an answer, we're going to ask our question. And with that question, we're going to look in a knowledge base, which could be papers from archives. In our case, it's going to be 32 papers on the AI's environmental impacts. And so given this question, we're going to search across those 32 papers. And we're going to find relevant passages that answer that question. So that could be quotes in the papers, it could be figures, it could be tables. You're going to retrieve all of that relevant information, and you're going to send that as context to your generation model. So this model is going to receive your question along with the retrieved context. And then it's going to finally generate an answer. So I think this is familiar to many of you, but hopefully this overview helps if this is your first time hearing about RAG. The overall idea is that we can ground large language model answers by providing a knowledge base. Any questions about RAG in general before we move on? Zoom or in person? Okay, I think we're all on the same page. Thank you, Claude, for the visual here. Quickly generated. So the evaluation setup here is we have 282 question and answer pairs that dig into the key insights of our corpus. That's the 32 papers that look at the environmental impacts of AI. Some of these questions require the AI system to just look at the quotes in the papers. Some of them require you to look at the tables. Some require figures. Some require some kind of math or simple reasoning. And then finally, some questions are deliberately out of scope. And then how we score across the entire chatbot system is we take a weighted score that looks at the accuracy of the responses. Was the answer correct? The reference overlap, so of the citations you produced, how many of those overlap with the ground truth known citations that are relevant to that answer? And then abstention recall is out of the number of questions that are truly not answerable, how many of those did you refrain from answering? Because we don't want you to answer questions that you don't have information about. That's the general idea. Just to give you a few examples very quickly, this is a question that requires the system to find this quote in this paper from Lee et al. 2025. Some questions are going to involve parsing tables from all these PDFs and being able to find the correct values for the question. Some questions are going to require some amount of visual reasoning. So here we're asking, what is the difference between these two lines at in the year 2020, I believe? Is that difference at least 10%? And then finally, some questions are going to require a bit of reasoning. So not just looking at the data, but can we actually draw some logical conclusions based on data across papers? So here the question is, the energy required to train a 6.1 billion parameter language model is equivalent to how many US household years of electricity consumption. So you need to find 2 data points, how much it costs to train a 6.1 billion parameter model, and then also what is the average US household consumption for energy. And then some simple math to derive the answer. How much does an elephant weigh? Your system should not know this because it's not present in the corpus. Okay, so that's the setup of the WattBot challenge. Are there any questions about that challenge before I move on? Pretty clear? All right. So we ran that competition for 3 months last fall. It was open to the public. We also had 20 people at UW-Madison competing. The winning solution, I think we had 96 participants total, was a gentleman named Shi Yang Ye, who's a CS master student. And he used Open Router. Is anyone here familiar with Open Router? A few of us. This is a tool that basically acts as what we call a model gateway. So you can fund your Open Router account, and it'll give you access to all the different large language model APIs, whether that's Bedrock, Gemini, OpenAI models. Just fund one account, and then you can use all of the different models. I haven't used it myself, but it looks attractive based on the features. And so he tested 7 different models, kind of throwing everything at the wall, hoping something sticks. And he was able to get up to 86% on the custom weighted score that I presented. So that's 75% accuracy, 15% reference overlap, and 10% did you correctly not respond when you were supposed to. So for the next 5-ish minutes, I want to quickly cover kind of the secret ingredients that led to that high score. So we're going to cover all 3 of these components. We have hierarchical indexing, multi-query retrieval, and ensemble inference. So the naive way to create what we call embeddings of our knowledge base so that we can search across it is to chunk up the papers into maybe length based on like a certain number of characters. So every 100 characters will be one chunk of data. Next 100 characters will be another chunk of data. If you split up your documents that way and treat that as your knowledge base, that kind of disrupts the structure of the information. And then that can lead to problems when you try to actually retrieve the information. So it's important to have structure-aware chunking. One way to do that is to split by sentences, not by number of characters. So that's what the winning competitor did here. They split up by sentences. So that's one thing to be aware of. That's structure-aware chunking. And then what they did is they took those sentence embeddings, and for each paragraph composed of sentences, they would create a paragraph embedding that's basically an average of all the sentence embeddings. Same for sections and same for documents. So this gives you a knowledge base that now has the sentence embeddings, paragraph embeddings, and section embeddings. And the benefit there is it sort of adds multi-resolution semantics. So you're not just storing the sentence semantics, the embeddings, you're storing the overall paragraph semantics as well. And so when you're doing that search, you could maybe hit on the paragraphs or hit on the sentences. Another kind of neat thing of how they set this up is when you do the retrieval and say you find this sentence as the number 1 piece of evidence, it will automatically unroll this and look at the preceding paragraph, the entire paragraph. So it expands the context. Now, we didn't do thorough A/B tests of like every method that we're going to show you to prove that it's going to work the best. But this is just a case study kind of presenting what worked well for this competition. Another component that we think is really relevant to the high accuracy here is the multimodal embedding that the author used. So you can create your knowledge base using either text embeddings or text image embeddings, so multimodal embeddings. Any ideas what the benefit of a multimodal embedding is? So not just text, but also adding images. What's the benefit? Yeah.
maybe disambiguating, like chicken, the cooked chicken versus chicken, the live animal. Like there's a ton of polysemy perhaps. And so you want to clarify like chicken as in this image of a chicken.
Maybe. I was sort of thinking in the context of trying to search across research papers, we have a lot of text in the papers, right? And that's valuable information. But we also have the figures, right? And in research papers, that's where the real data is. Sometimes the words are lies. And so we want to look at the figures, perhaps only the figures. And that's where we're going to gain the most knowledge. So in order to do that, we need a multimodal embedding that can code those images so that our large language models can understand them. So one multimodal embedding model is the Gina v4 model. There's a bunch of them, but this is one of them. It's open source. It's part of the Quen family, which is from the company Alibaba. This is a 3.8 parameter multimodal embedding. It can produce feature vectors describing your knowledge database, your papers. Those vectors can contain up to 2,000 dimensions, so 2,000 different features. You can also use smaller ones if you want to speed up the time of your RAG pipeline. So in our experiments, we use 1,000 dimensions. And the whole RAG idea is ask a question and then retrieve relevant chunks. So how do we do that mapping between questions and chunks? Any ideas? It's on the board. Contrastive learning. So contrastive learning is when we train a model to kind of map pairs of data. So we can take our query and try to map it to relevant context. And that's what we do with contrastive learning models. You're going to train it on millions of pairs so that you can do this sort of mapping. So that's the magic behind ask a question, find the relevant evidence. It's going to use contrastive learning and an embedding model. And that's kind of depicted down here. We're going to embed the entire corpus into chunks, embed the question. That gives you 2 feature vectors. Well, that's 1 feature vector. That's a bunch of feature vectors. And then you're going to search across the entire corpus and your question, and you're going to find the top K most relevant pieces of evidence. So it boils down to linear algebra, like everything does in machine learning. Okay. Another component was this query planner. So the idea is rather than just ask one question, ask a large language model to take your question and convert it into N questions. That sort of capture the same overall idea of the question, but maybe use slightly different terminologies, try to ask it in a slightly different way. So the idea here is, can you please rephrase your question? And that's going to allow you to retrieve slightly different semantics. And so if multiple queries independently retrieve the same passage, that helps improve the likelihood that that passage is relevant, right? So multi-query planner. We also have ensemble voting. So what's better than one large language model? Multiple large language models. So we're going to use several different models, run them through our entire pipeline, and try to get their answers. And then we're going to look across all those different answers and take the majority vote. So what was the most common answer? Let's use that as the final response. Then finally, one extra piece here is iterative deepening. So if you ask a question and the question is out of scope, or the model doesn't find enough evidence to answer it, we try iterative deepening, meaning we actually expand the amount of evidence that we retrieve, and then we ask the question again. And we do that up to 3 times. Trying to balance the efficiency as well as the accuracy of the responses. Okay, that's the overview of the winning solution. So I'd like to pause for questions, but moving us along here, we're going to hand things off to Blaise Enuh, who is a research associate in the Great Lakes Biotech Center, right? Bioenergy Center. And he's going to tell you about recreating this entire experiment locally using some on-prem compute options. So hand things off to Blaise. While he's setting up, are there any last questions?
Yeah. So in the retrieval, if you retrieve contradicting evidence, do you have any recommended way to solve this issue?
Well, I mean, it's all basically comes down to cosine similarity. Whatever evidence is most relevant to the question is going to come to the top because we look at the top k vectors.
How about one evidence say yes, the other evidence say no?
Yeah, we're not completely dealing with that
Oh.
here just yet. Come to tomorrow's paper discussion though, because that is dealt with a little bit. Yeah, because when you're looking at larger corpora across a longer time scale, the findings will change over time. So you kind of need to figure out how to deal with that when you're trying to extract scientific information. Good question. All right, I think so. Blaise.
Okay, so adding to everything Chris has talked about already, so the entire rack system, we want to try running this on a local setup and on the cloud as well. So I look more on the side of the local setup, and for the local setup, we're lucky to have two options. One with the Dell Pro Max, a GB10 with some quite interesting specs, and another setup with the PowerEdge RS7725. So, so the pipeline is basically the same pipeline Chris has talked about, but you'd notice that at the level of the generation, that's where we input the architecture for the local setup. So, and Chris talked about Open Router as the LLM provider for the original WattBot system. And so we are replacing that with models from Hugging Face. And we mainly use the Quen model family of models to try this locally. And then with that, we look at the answers that are generated and we do some analysis on that. So the entire experiment revolved around the modifications we did here and how it impacts the answers that we're going to have. And so just to give a small overview again on the devices that we're using, as Chris mentioned before, the Dell, the GB10 has a 128 gigabytes of unified memory CPU plus GPU and a performance of 1 petaflops. The way I kind of think of petaflops, or at least from what I read, is the computation that a human being would typically do in 32 million years, I think so. So that's kind of pretty efficient. And it's got 20 cores, but most importantly is, why is it that we're using this for our setup? So the memory itself is pretty good. It's a good enough memory for us to run a couple of good models like Quen, DeepSeek. And also, we can run models for theoretically up to about 200 parameters for inference and fine-tune up to 70 billion. And for the PowerEdge, we have about 192 gigabytes of RAM. It's got for the 8,000 cores, roughly split between two CUDA GPUs. And we also have 384 cores for the processing. But also it matters for our setup because, again, we have high performance and it's also optimized for storage and for the kind of AI work that we want to do. And of course, it's scalable as well. So for the experiments that we did, for the most part, we use Quen models. And for those who don't know what Quen models are, these are a family of transformer-based LLMs that were developed, or at least are developed by Alibaba Cloud. And they are open source. And so we can use them for different tasks that we want. And the configuration, the weights, and several other information about the models are provided. And it's got support for so many other languages, which could be useful if we're looking at a corpus where it's not just English, but maybe some other languages, papers from other languages. But also that the models have hybrid thinking modes and quite a huge context length. So if we have queries that are long, or we need inputs that are quite long, these models are going to perform really well on that. And there's also the benefit that they have the mixture of expert architectures that helps in reducing memory and compute costs. And that's also great for the setup that we are trying to look at here. So, and there are multiple size options, so you can kind of test across different sizes and see which ones kind of fit with your resources. So let's look a little bit, let's take a look at the results of the experiments that we did. So you'll see that we started with Qwen 1.5 and up to the Qwen 3 next generation models. And this graph essentially shows us how the score of the competition, how the different models performed on the score. So if you remember, Chris talked about the different weights and how the scores are calculated, 75% on value and 15% for references and 10% for questions that they couldn't answer. So the general score for the different models, so starting from about here, we see that the Qwen 2.5 models up to the Qwen 3 next generation models have, there's a kind of a little competition for the scores. We have 0.8, but the differences are in like 2 decimal places. And the overall accuracy drops as you go from the, for example, the 1.5 performs the least, and the other 2.5 models with smaller weights, smaller parameters kind of performed a bit less, but the more recent models are performing better. But we also noticed that individual models, like very performant individual models like the Qwen 3 next generation, outperform ensemble, the ones that are made from ensembles. So that was a pretty interesting finding that we made. And this is probably going to be good for us because as we'll see in the other results, this gives a lot of information that will help us to set up our system really nicely. And so that was the general score. But now we want to look at how these models performed on the different components that made up the score. And so the green is for the value accuracy, and the blue is for the reference overlap, and the purple is the recall on the unanswerable questions, and the red is the overall. So again, one of the reasons we might attribute the high scores, the Qwen model scored really highly, was probably because the recall is highest, where it scored the highest compared to the other models. But we do see that when it comes to references, retrieval, all the LLMs kind of perform almost comparably, with the exception of the really smaller models and the older generation models, family models. And so, so from this graph, we can kind of say that the architecture for the Qwen 3 next generation models was probably better, helping them recall more on questions that were not answerable, and as such help with the accuracy. And remember that for RAG, not giving false responses is really, really important for the entire pipeline. So that was a pretty interesting observation that we made. And now, if we are scaling the models to really big sizes, what does that do to the speed at which you can retrieve our answers? So generally, we still do the comparison between the Qwen family models, and you can kind of see that with the 2.5 family models, and as the number of parameters increases, there's kind of a linear increase in the latency, and 1.5 is kind of an outlier, which shows that at least with the increase in the improvement in the architecture, the models have tend to perform a little better. But we also see that the Qwen 3 30 billion parameter model also has a fairly good, well, probably the highest latency, but compared to the 1.5, it performs really, really better. And then we have right up there the Qwen 3.3 next 80 billion parameter family model, which in a way also kind of gives a linearish increase in latency for the Qwen 3 family of models. So ideally, we want to look for a sweet spot, but we can look at the other results from the experiments to see what that is. So we want to also look at the model size and how this affected the entire WattBot score. So this would probably tie with the first graph that we see, but we also, so here we generally see that in the middle here we have the Qwen 2.5 family models and the Qwen 3 that share somewhat similar scores, but in a way, it seems more like the higher the model, the higher the number of parameters, there's kind of reduction in the accuracy, the increase. There's kind of a reduction in the accuracy over time, probably going to plateau for some reason. But then we still have the Qwen 1.5 model that's an outlier, performs really, really, has a lower score compared to the others, and it's a very, very big model. So again, we can kind of see here that architecture, the improvement in the architecture for the models. So the Qwen 3 models have a better architecture, improved mixture of expert architecture. So it's probably due to that that the performance tends to be a bit higher.
Blaise, real quick, I think the training data was also different. So that could be
right. So, but also right here again, we see that the 3.5, the Qwen 3 and the 2.5 have, there's this tie with the number of parameters. So let's look at so in terms of size and GPU energy per experiment, again, we have the 2.5 family models that have some kind of a linear increase in GPU energy consumption as parameter sizes increase. And we have right up there the Qwen 1.5 family of models. So again, a better architecture also helps us reduce the energy consumption with the models that we're trying. But probably more importantly is like I talked about a sweet spot in the start. Here we have the 2.5 model and the three family models, but also we see that there's this really big, almost a twofold, 2 times increase in GPU energy consumption. So in my opinion, at least for the score, the trade-off for the score here is probably 0.02, I think. So if we're looking at GPU consumption and the size of the models, and maybe we want to talk about, we are doing an experiment on energy usage. So it might be a good idea to start looking at models that have this parameter size and energy consumption if you want to look at trade-off. So
quick comparison. So I don't know if anyone here knows, but the average energy cost of running like your dishwasher is 1 kilowatt to 2 kilowatts. So the black dot up there is like running your dishwasher once,
which is the Qwen 1.5. So
300 questions also.
Yeah, so this is basically a summary of what we got with the local setup. I don't know if anyone has a question. Yeah.
I have a couple of questions. On a couple of your slides, you mentioned 4-bit models. What's a 4-bit model?
So my understanding of the bits are the quantization thing at the level of the floats. So you have models. So you have these. So the weights of the models can be in float numbers like I'd say 1.2345677, really long decimal points. And with the 4 bits, you kind of bring that in, you reduce that in a way that it uses less memory on the chip. So by reducing the decimal points, you can consume less energy on the chip, and it's a little bit more efficient. That's how I can understand it.
I see. And so the precision to like the 100 decimal number doesn't really matter, right?
Yeah, well, typically it's
Yeah.
like 4-bit, 8-bit, or 16-bit.
Alright.
Yeah, typically the 16-bit models, at least for inference, you don't need the full precision. When you're
Uh-huh.
doing training, that's when you do want the full precision. Otherwise, things can not train as well.
I see. Also, on this slide that compared performance of different models, you had your different quant models, and you also had ensemble models.
Yeah.
What's in the ensemble model like in your case? Is it the same as the winner of the competition, or is it a different thing?
So the ensemble models, we use models that we could have access to on Hugging Face. So not the models that were used in the original RAG system. Well, he bought some of them, are paid for on Open Router. So on HF Hugging Face, we don't have access to all of those. So that's why we used mostly the Quen, because they're really good and they're open source and we can have access to them.
So ensemble just contains other than quant, but other models that are accessible as like
Yeah, right.
It's all from these models that you're showing here. So we take like the top 3 of these, or the top 5.
Oh, so you just take like the top 3 quant models, right?
Yeah.
That's your ensemble. Why you do it that way as opposed to like take, I don't know, Llama or whatever?
Well,
as a
hopefully for
model.
convenience at this stage of the movement. But we do, if you look at the previous slide with the ensemble, if you want to pull that up real quick, please, the ensembles don't do better than the single models here, and it's probably because the ensembles aren't diverse enough.
Yeah.
All right. Yeah.
Yeah, the ensembles do better when you have the wisdom of the crowd, right? So you need to have slightly different answers, different models.
Yeah.
Okay. Thanks.
So the slide, the other slide,
The one before?
the next one. Yeah.
This one?
So it's really interesting. So it's clearly corollary that the size of the model is costing more. Did you look at the amount of memory being consumed on the GPU itself to see if there was a corollary between the amount of memory consumed and the amount of power being drawn on that system?
So for that, we didn't look at that, but my hypothesis would be that so the Quen 3 models have the mixture of expert architecture. So say, for example, we have 70 billion, but you have like 2 billion active. So you would actually think when you're running a token, or you're trying to run a pipeline, you have just the 2 billion active that are going to be loaded. But it feels like maybe it loads all the 80 and then keeps the other ones active. So that process of doing that makes it a little bit more so it still kind of loads the entire thing basically, and I guess it's going to consume more energy for that reason. But that's kind of how I
It's a good question.
think about it.
How complicated it would be actually.
Yeah.
Kind of like
And that was my follow-up. Exactly. That was my follow-up question. It's like the size of the model and the amount of memory you have, just because the memory of the model gets consumed in the system, but then you also have the inferencing that's happening inside that model.
Yeah.
That's happening inside that GPU. So like that amount of memory is going to shrink, and you're going to have more context switching within the GPU, which should drive up the power because of that. So that's why I was curious if you track the amount of memory usage on the given GPU. I think that would be a better and more accurate representation of instead of saying the model size, the amount of memory being consumed on the GPU.
Yeah.
I think that's a good point.
Another way to say that is it's going to be highly coupled with the runtime, and the larger models are going to take longer to ingest and generate the responses. So that's going to be another factor. Yeah, it's a really good point.
Yeah.
I think we need to move along for our next presenter here. So maybe one last question while you trade minds. Guy, do you have a question?
Yeah, I had one. Like, what is your experiment, like in those, like whatever, 232, whatever?
What is the,
Yeah, where you define the experiment? What is the experiment? Is it just like really initial prompts, like at like?
we have 280 questions that
Yeah.
dig into the key insights from across 32 papers that are looking at the environmental.
That is the experiment.
That is the experiment, yeah. All right. So next up, I'll hand things off to Nils Matteson, who's a CS and data science undergraduate. Yeah, so thanks, Chris and Blaise. So as Chris said, Nils and my role on this project was building out the AWS Bedrock pipeline. So Chris and Blaise just kind of walked you through the Kohaku RAG and how it won the Kaggle competition. And my job was pretty much to take that pipeline, deploy it on AWS Bedrock, and answer the question of if you want to run a RAG system on the cloud without managing any GPUs, which LLMs should you be using? So I guess if you're not familiar with AWS Bedrock, I mean, it's Amazon's managed inference service. So with one API, you can hit models from pretty much all the major providers: Anthropic, Meta, Amazon, DeepSeek. And basically, we tested 9 models and 3 different ensemble strategies through the same API. So with the exact same retrieval pipeline underneath. So that's kind of the only variable in that was the model generating the final answer. So I built the initial Bedrock integration, ran the first rounds of benchmarking, and then fixed a couple bugs along the way in the scoring and validation pipeline. And then Chris reran the experiments with an updated pipeline that kind of better matches the original winning solution setup. So these are going to be the results that I'm going over. So just first and foremost, I kind of want to go over the pipeline architecture. It's pretty similar. We kind of talked about this a bit earlier. We take the PDF corpus and we embed it. But I want to make a note that for the Bedrock deployment, we actually switched to Amazon's Titan v2 embeddings. The winning solution actually used the Gina v4. So yeah, I just wanted to make a note of that. I'll discuss that a little more in a second. But yeah, we pretty much have the exact same setup here. We have the 4-level hierarchy, query planning, and then deduplication, re-ranking. So yeah, the key thing here is that everything upstream of the LLM is pretty much identical across all experiments. Same embedding, same retrieval, same re-ranker. So hopefully all the differences should be purely about the generator model. Yeah, and then just about Titan v2, one thing I wanted to make a note of our design choice here. This is just the embedding model that runs natively on Bedrock. Means that everything runs in the cloud with like 0 local GPU requirements. And this was a deliberate choice to make it fully serverless, but there's kind of a caveat. So Titan v2 is actually a text-only embedding. It doesn't understand images or figures or anything, which is obviously kind of a big part of the corpus. So if we chunk a PDF and hit a figure, the embedding is going to capture the caption and maybe the surrounding text at best. Like if you like a little bit of that. But the actual like visual content, like interpreting a graph, for example, that's lost. So keep that in mind when we get to the accuracy by question type results. You're going to see that the figure-based questions are kind of where every model struggles here. So I think going forward, we suspect that a multimodal embedding, like Chris talked about, image and text, which is what Gina v4 is, could definitely improve our scores quite a lot in that department. So this is pretty much the headline result of the Bedrock models. Like we said earlier, this is based on 75% value accuracy, 15% reference overlap, and then 10% unanswerable or NA recall. We ran all the same 282 questions from the test set for each model, and then 3 different ensembling strategies, which are listed here.
And then I think the first thing to notice is that the ensemble methods are pretty obviously topping the chart. Looks like we got about 0.84 and 0.83 for the top, which we're pretty happy about. This, I think, is a good demonstration of wisdom of the crowd effect here, going with the same kind of top K models for the ensembling. And then among the single models, it looks like Anthropic's Claude 3.5 Sonnet is kind of doing the best on its own, which is, I mean, essentially tied with some of the ensemble models. And then you have models like DeepSeek and Llama 4 Maverick kind of closely sitting together. And one thing that was most interesting to me was 3.7 Sonnet actually ended up scoring the lowest, which seems a little weird that, you know, the latest and greatest model would kind of do worse than 3.5. But we'll come back to that later. It has a little bit to do with the refusal behavior. But I feel like the overall takeaway here, though, is that the spread's pretty tight. You know, they kind of gravitate between 0.75 and 0.83. And it looks like the retrieval pipeline's kind of doing the most work here. So like with the local models, this is kind of the composite scoring for each experiment. Like we said earlier, each model has 4 bars. We have the value accuracy in green, reference overlap blue, NA recall, which is like unanswerable in purple, and then in red, just the overall scoring metric. So I think the reference overlap is interesting in this graph. It looks like 3.7 Sonnet actually had the highest reference overlap, which, if you can see, is about 0.92. So that means that it's really excellent at citing the correct source. But its overall score is kind of low because, not because it gets the answers wrong, but because it refuses to answer too many questions, which kind of tanks its value accuracy. So I would say that the NA recall here probably varies more than in my earlier runs. Most models are in like the 0.8 to 0.88 area, and feels like the ensembles are pretty consistent, which I feel like is why they score pretty well overall. So I feel like if you care about traceability and you want to be able to verify where an answer comes from, the reference overlap definitely matters. And it seems like the Claude models have an edge there, even if their overall score isn't necessarily the highest. So yeah, this graph is breaking down the performance by question type. We have the 5 categories at the bottom for the 5 different categories of questions that we have, along with their sample sizes. It looks like, here quote-based questions are definitely the easiest for most models. They seem to do pretty good at that. So it looks like the retrieval just is pretty easy, and the LLM is able to pull out an answer from that. Table questions, kind of moderate, I feel like parsing a tabular data structure is probably a little bit harder, so I feel like that makes sense. And then, like I said earlier, the figure questions are where kind of everyone struggles. And I think that's kind of the most important insight on this slide. The bottleneck isn't necessarily the retrieval, or it is the retrieval, not the LLM. So, if the pipeline can't really retrieve meaningful content from a figure, so nobody can answer that correctly. So I think that testing out different embedding models would definitely be something to explore in the future. And then, yeah, NA detection is pretty good overall. One thing to note, I feel like, about the math is there's a pretty small sample size on that. So I feel like maybe be a little weary of those results. That was a little surprising to me. So this is kind of the cost performance graph that I came up with. The x-axis, it's the total API cost of running the full 280 question benchmark, and then the y is the overall score that the model got. So Claude 3.5, clearly the winner, did really good, but it also cost almost $30 to run that entire pipeline. But if you go ahead and look at Meta's Llama 4 Maverick model, that only costs about $4 to run, which I found interesting. And you're basically getting about the same performance for like 7 times less, which is pretty cool. I feel like kind of the middle of the road models are DeepSeek R1 and the Nova Pro, about like $13 and $8 respectively. So I feel like that kind of seems mid-range. And then 3.7 Sonnet was the one that just absolutely tanked. You get the worst performance for almost the most expensive price. So that was definitely the over-refusal problem. So I guess the practical implication of this is if you're deploying these things at scale, in my mind, I feel like Llama 4 Maverick, which is a mixture of experts models, kind of gives you the best bang for your buck in that regard. Then just going over the latency versus model size. Clearly for like an interactive application, the latency really matters. So this kind of just, plots those two things. Fastest, ironically too, and most accurate were the Llama 4 Maverick, which took about 3.5 seconds, and the Llama 3.3, 70 million. Mid-tier is kind of like Sonnet and DeepSeek, about 13 to 15 seconds. It's not horrible, but you'll definitely feel the latency. But it's usable if you kind of want to make that exchange. Then once again, Sonnet clearly is struggling in this department, 30 seconds per question. And I think this might have something to do with the models, the whole chain of thought reasoning, before it really generates a result or an answer. So for our Streamlit demo, I would say that the Llama family and Maverick in particular kind of gave the best interactive experiences when you're trying to balance strong accuracy with low latency. So kind of to address the elephant in the room, looking at the refusal rates, because 3.7 Sonnet was our best model in earlier testing rounds when I did some tests, and I was kind of expecting it to lead on the full benchmark. So I was kind of like, what happened? But clearly, as you can see, the issue is that it refuses almost a quarter of the questions, whereas every other model is between 6.7 and 11.7%. So that's kind of weird. It seems like Claude's safety and uncertainty calibration is a little bit too aggressive for our implementation here. I guess it sees like a ambiguous retrieval context and it just chooses to abstain rather than risking a wrong answer, which I feel like is pretty reasonable behavior in most production settings. If you want a model that says, I don't know, rather than, hallucinating and guessing. But, in a second benchmark, every refusal is 0 on that question, and it just totally tanks the score. So I thought this was kind of an interesting and good lesson to anyone who might be wanting to deploy a RAG application. Kind of depends on your use case because, the safest model might not always be the best scoring model. So you kind of need to match the model's refusal threshold to your use case. So just kind of wrapping up here, I just want to talk about kind of the first takeaways that I thought. I think firstly, ensembles clearly work. Top 3 majority voting was the best score kind of all around. And I think if you can afford the latency costs of running multiple models, the wisdom of the crowd, it consistently outperforms any just individual model. And then secondly, I feel like Llama 4 Maverick really impressed me. It seems like it's kind of the sweet spot for single model deployment in terms of latency and accuracy and price. I thought it was interesting how this was a mixture of experts model with only 17 billion active parameters. So I think that's kind of cool that it's just fast and cheap. And then third, just overall, prior to this, I had like limited Bedrock experiences, but it made multi-model comparison really, really easy. You know, it's the same API, same retrieval pipeline. You just kind of swap the model ID. And I just kind of feel like there's a lot of value in managed inference APIs. And then fourth, you know, I mean, figure questions are really hard for models. I think the retrieval is clearly the bottleneck, and that has a lot to do with our Amazon Titan embedding that we chose to use. So that's definitely something that I think would be interesting to explore in the future, to see how that implements or fixes things. And, you know, I thought the whole lesson learned about 3.7 was definitely something interesting as well, and kind of being able to assess model performance based on your use case. And then, do you want to handle this slide?
Yeah. Any questions for Nils while we're handing off?
Yeah.
So when you measure have one number, if you were looking at something like precision and recall, for example, would the Claude 3.7 have high precision and low recall, or like sensitivity and specificity, you know, like low sensitivity, high specificity? Is that what you would get?
I think so. I think that would propagate it to low recall. Yeah.
Yeah.
It's like summarizing performance as a single number is like
Yeah, I mean, basically, the abstention recall is kind of like a recall metric in our overall score, but it's just looking at the unanswerable questions.
Right.
Yeah.
In AWS, we didn't have the multimodal embedding. Like we just had.
It is an option. We just haven't tested it yet.
You haven't, because you didn't want to spend like.
Well, no, the money is fine. It's the same cost. We're just we're A/B testing things. So yeah.
Yeah. I think, did you have a question?
Yeah, it looked like the Claude or the Sonnet one that you said refused to answer a lot of questions. I'm not sure if I'm remembering this correctly, but it also got a bad score on the questions it was supposed to refuse to answer. Is that right? As in, like, it answered some, like it both refused to answer a lot of questions, and it also tried to answer some that it shouldn't have been able to.
Now that's both the is and a component, but the value accuracy, we had that bar, and that bar was relatively similar to the other models. So its actual accuracy was relatively comparable, maybe slightly above some of the other models, but the is and a thing was much lower. Yeah.
Yeah.
So have you?
Question about is there a reason you didn't like test or want to test OpenAI's?
OpenAI was not available, I think.
Well, it is actually. We did some. Do you want us to talk about your preliminary test and you play around with it?
Yeah. I definitely played around a little bit with. I think I used OSS 120 billion a little bit, honestly.
Yeah, I had a small 50 question test set that we were just exploring models with, and it didn't do that great, so we just cut it off the list to save a little bit of money.
Yeah,
but yeah.
Interestingly, though, I think the paper used that model.
I saw that mentioned the OSS one.
Yeah,
20 billion. Yeah,
but it performed really poorly on kind of the preliminary test that I did, so we kind of decided to run with other models.
I think we haven't excluded it yet. It's worth looking at, especially when we add the visual embeddings back in. That'll be interesting. Yeah.
So I'm wondering what does better, Llama 4 or Quen? Have you compared it to
maybe if we're gonna run over time by a few minutes, but if you all feel like sticking around, I'll cover a little bit of cross system comparisons. So this is looking at the latency of all three. Green is Bedrock, blue is the PowerEdge, and yellow is the GB10 hardware. So Bedrock is clearly the fastest. It's like 10 seconds per question. If they weren't the fastest, they probably wouldn't have a successful company right now. So it makes sense that they're doing really well. The PowerEdge is that 2 GPU server that we have from Do-It that we're playing around with. And you can totally host RAG on the PowerEdge. It's not going to be entirely ideal once you get to larger models. Then it's going to start to take like 60 seconds per question. Not ideal, but you could do it. The GB10, not really feasible for long-term hosting of RAG. I treat the GB10 more like a development workspace for testing things out when I don't feel like paying for the cloud. But really, you probably don't want to host things long term unless you're using really small models in like the 77 billion parameter range. The results were actually pretty comparable across Bedrock and across the local experiments. So we got around 84% as the highest results. Bedrock is faster. The Dell PowerEdge is not too far behind. Develop on GB10. Cost would be the other big consideration, right? So we showed you that Bedrock does cost some amount of money, especially for the really expensive models. It could be like $30 to ask 300 questions. But we found in our experiments, the middle of the road model, which was DeepSeek, was only $13. And that's for 300 questions. So it's really not that bad. And then again, I want to remind folks, if you are running things locally, there is still a cost. It's just not in your wallet. It's going to cost some electricity. And also your GPUs can become outdated. So that's another concern. And then finally, we do plan in the future to add those visual embeddings. We're expecting to get above 90% once we do that. Because really all the bad results we got were mostly figure related. Any questions about our experiments? Otherwise, I'll show you what this looks like if we host the entire system on Streamlit. I'll pull it up. But yeah, last questions. Sorry for speeding through the summary here. Round of applause to Blaise and Nils for their experiments. And then if I can just really quick show you, I have got a Streamlit app set up so that we can actually host this chatbot system. I can say how much energy does it cost to train a large language model? And it's Bedrock, so it's going to take like 10 seconds. We were reporting the cost here. That cost me a penny and a half. And it's giving me the answer, it's out of scope. So that's actually a feature, not a bug. I'm going to add this allow best guess toggle and then ask the same question. So that even if the system says I don't want to respond, we can kind of force a response. We'll be releasing some documents along with it. So if you're interested in hosting your own RAG, email me, endeman@wis.edu, and I'll get you our GitHub repo. And also just check ML+X Nexus, and we'll be sharing this talk recording as well as all the GitHub stuff. Thank you.